Hello students, today we're going to be opening a new series on algebraic number theory, and we're going to be following Frazer Jarvis's textbook. I'll attach a link to the file in the description along with our Discord server, and we're going to spend this whole series building towards some genuinely deep results, but every single one of them trace back to one idea we're going to be unpacking today. But before we open the book and discuss any content, here's the map. We're going to be building a five-chapter spine on unique factorization, number field, discriminates, ideals, and prime ideals, um, ensuring that the foundations are completely solid because chapters 1 through 5 are pretty fundamental and nothing after them work without him. And once we reach chapter 5, instead of taking the long way through quadratic fields, geometry of numbers, and small degree fields, we're going to be jumping straight to chapter 9, 10, and 11, which consist of cycloatomic fields, Fermat's last theorem, and some other exciting information. And that's the summit for this series. Chapter 6 through 8 aren't going to be gone. We're just going to be deferring them and circling back after this initial climb. So, and aside from that, we're going to be going off of the content covered in Stanford University's math camp as well, specifically their structuring of their program 1, which is on algebraic number theory and abstract algebra. So yeah, aside from the number theory course, we're also going to have an abstract algebra series that's going to be running in tandem with new content and some overlap. And aside from that, this series is going to be run with two instructors, one myself, and the other my friend Orion. And I'll attach our Discord handles in the description if you want to contact us. And this series is going to have around 40 videos, give or take. So today we're going to be starting out with chapter 1. And you can see here, this is what the logical spine of this video is going to be surrounded by. And we're going to start with something that feels almost insultingly simple. We're going to be looking at, first, the prime factorization of 360, right? And what is that? That is the product of 2 cubed times 3 squared times 5, right? And you've known this since grade school. And sure, you can write it out in different orders, right? So 360 can also be written with its full list. And it can also be written out with, some negative numbers as well. So negative 2 times 5, 3 times. So you can shift around the order and the signs in certain ways so that you're left with the same number in the end, 360. But you immediately recognize that these, you can recognize these as the same factorization. There's nothing new there. And here's a trap, right? It took mathematicians until the early 1800s, specifically Gauss, to realize that this uniqueness is not automatic. And it's a genuinely special property of the integers, and it requires proof. And by the end of the series, you're going to watch it fail completely in other number systems that look relatively the same or even almost identical to the set of integers. So today we're going to be building the machinery properly, which is going to consist of the primes, Euclid's algorithm, and the fundamental theory of arithmetic. And we're going to get comfortable with exactly why each piece works, because in a few videos later, we're going to watch the same argument collapse and understand the collapse is the entire point of the book. So once again, here is our path for today's video. we're going to be looking at the 5 stepping stones, which are divisibility in primes, the greatest common denominator, Euclid's algorithm without identity, one key lemma about primes dividing products, and then finally the fundamental theorem of arithmetic itself. And you can reference this logical spine as we go out. And by the end, you'll have the whole chain constructed from scratch, plus a clear sense of the single fact everything else quietly depends on. So, start out, we have 2 definitions to anchor everything. B divides A, written here. If A is equal to BC for some integer C. A prime number is greater than 1 whose only divisors are 1 itself, right? And these seem simple enough, but we're going to see later on why these definitions matter. And also, yeah, and I guess a side note is if n does not equal 1, well, I guess like the opposite of this, right? We call this a composite. But yeah, moving on. Now we're going to be looking at Euclid's theorem, which is basically saying there are infinitely many primes. And the proof for this is a pretty beautiful contradiction. Suppose there were only finitely many primes, right? So for the sake of contradiction, we can write this as P1, P2, and then all the way to the Pn, right? That means we can build some number, right? Some number n, I guess, to be the factorizations with these limited numbers of primes, right? And every integer greater than 1 has at least one prime factor, so n has a prime factor of p. As, yep, once again, every integer greater than 1 does. But notice here, right? N is exactly 1 more than a multiple of every prime factor, right? Of p sub I on our list. So just notice here that p sub I does not divide n for every I. That means p is different from all of them. And I guess to specify, right, for p sub I, that means n is congruent to 1 mod pi. Yeah, that means p is different from all of them. And we've produced a prime that wasn't on our complete list, right? So this case with the plus 1 at the end for this n produces a contradiction. And we've found that p is different from all the other primes, and we've produced a prime that wasn't on our complete list. So that's our contradiction. So therefore, there must infinitely be many primes. And hang on to this proof technique, building a number specifically engineered to dodge a finite list is a trick that the textbook by Jarvis has you reuse in future exercises to prove infinitude for primes in specific congruent classes. So I guess to summarize, right, no pi divides n, so p is not an element of this finite list of primes. And then that is our contradiction. Now we're going to be looking at the greatest common denominator, sorry, the greatest common divisor. or denominator. Um, and basically, the definition is the greatest common divisor of two numbers a and b, we'll say as h, is the largest integer dividing both a and b. And when that greatest common divisor is 1, we can call a and b coprime. So I guess I can write here equal to 1 coprime. And the divisor algorithm lets us write a is equal to q times b plus r, with 0 being less than or equal to r, which is less than b. And the key theoretical fact, which is lemma 1.7 in the textbook, is that the greatest common divisor of a and b and the greatest common divisor of b and r are actually equivalent. Dividing repeatedly never changes the greatest common divisor. It just shrinks the numbers, and that's the entire engine behind Euclid's algorithm. So let's look at an example here of computing the greatest common divisor of 630 and 132. So we can start off with 630. What's the most straightforward? I guess the first thing that comes to mind is 1 times 132 plus 102. And by lemma 1.7, right, following the same structure, the greatest common divisor of a and b has to equal the greatest common divisor of b and r. So now we have to find the greatest common divisor of that. So to keep on going, right, 132 is equal to 1 times 102 plus 30. And then going forth, we have the greatest common denominator of 132 and 102, and 102 and 30 are the same. So that means 100. Now we find the greatest common divisor of 102 and 30, right? So 102 is equal to 3 times 30 plus 12. Following the same logic, we see that 30 is equal to 2 times 12 plus 6. And finally, 12 is equal to 2 times 6 plus 0. So now we have a remainder 0, and we can stop. So the last non-zero remainder is 6. And this chain of divisions is Euclid's algorithm. Each line shrinks with shrinks the problem while keeping the greatest common divisor fixed, and it terminates relatively fast. Now we have the interesting part, I guess, like the payoff, which is we can run the algorithm backward. So starting from the second to last line, right? 6 is equal to 30 minus 2 times 12. If we do a little bit of rearranging here, we can substitute the previous line's remainder in for each term, right? So take some time to notice this, right? You're simply taking the remainder, the previous line's remainder, in for each term, and then working back up to the original numbers. Yeah, so that's equal to that. This is equal to this is equal to 132 minus 102 minus 2 times 102. That's equal to 7 times 132 minus 9 times 102. which is equal to 7 times 132 minus 9 times 6, 30 minus 4 times 132, which is equal to 43 times 132 minus 9 times 630. Yeah, we've finally found the original list, right? And this is we found a explicit integer combination, which is basically 6 is equal to negative 9 times 630 plus 43 times 132, where s is equal to negative 9, t is equal to 43. And this is actually theorem 1.9 in the book, which is otherwise known as Bezout's identity, which is for any a and b, there exists integers with a and b, set of a and b, such that the greatest common divisor, or I guess just the set, is equal to SA plus TB. And it's not just an existence fact. We just watched exactly how to construct S and T by hand. And in the previous case, right, we saw that the greatest common divisor of the previous case, which is 6, is equal to negative 9 times 630 plus 43 times 132. And we just found those integers S and T. So now we have this other example, which I suggest you try to do yourself. And you can pause the video here. We're trying to find the greatest common divisor of 999 and 700, right? And I'll skip the work. We'll find that the Bezout coefficients, we'll first find that the greatest common divisor turns out to be 1. So 999 times S plus 700 times T is equal to 1. And running the algorithm all the way down, the greatest common divisor, turns to 1. So that basically means that 999 and 700 are co-prime. Back substituting gives us S is equal to negative 233 and T is equal to 333. And just a quick note, Bezout coefficients aren't unique, so if your numbers differ, check and make sure they still satisfy the equation. And that gives us corollary 1.10. I guess, okay. I'll just write out the work really quick. 1 times 700 plus 299. 700 is equal to 2 times 299 plus 102. 299 is equal to 2 times 102 plus 95. 102 is equal to 1 times 95 plus 7. 95 is equal to 13 times 7 plus 4. 7 is equal to 1 times 4 plus 3. 4 is equal to 1 times 1 times 3 plus 1. And then finally 3 is equal to 3 times 1 plus 0. So this running the algorithm, that gives us corollary 1.10 for free, which is A and B are co-prime if and only if there exists integers S and T with SA plus TB is equal to 1. And we just watched both directions of that in action. And here's the lemma that actually makes this work. If a prime P divides a product AB, then P divides A or P divides B. The proof leans directly on what we just built, which is if P does not divide A, then P and A are co-prime. So so if P and A are co-prime, by corollary 1.10, there exists S and T with SA plus TP equals 1, right? And if we multiply through by B, you'll have this expression. And since P divides AB, it divides the left side, hence the right side as well. So by this statement, we arrive at P divides B. And if you apply this repeatedly to a product of many terms, you can get corollary 1.16, which is if P divides a product of several integers, it must divide at least one of them. Now we move on to the fundamental theorem of arithmetic, which is every integer greater than 1 factors into primes in exactly one way up to order. So suppose for contradiction that for some n, that some n have two genuinely different factorizations. So suppose n has two factorizations for contradiction. We can write this as product of P1, P2 to the PR is equal to the Q1, Q2 to the QS, where no prime on the left also appears on the right. So there's no sharing of primes on each side. So P1 divides the left side, right? As stated earlier. Because of that, it has to divide the right side as well, because it is giving the factorization for the same number. So I'll just write P1 divides the right-hand side. And by corollary 1.16, P1 must divide one of the prime factors Q in there. So what that means is P1 has to divide some Q sub I, Q sub J, for some J by corollary 1.16. And since Q sub J is prime, its only divisors are 1 in itself. So that basically means P1 has to equal QJ. And that directly contradicts our setup, right? Because the earlier assumption means that no prime was shared between the two sides. So this is our contradiction. And no such counterexample can exist. Factorization into primes is unique. So if you go back to our very first example of 360 equaling 2 times 3 squared times 5 from the very start of the video, that's how it turns out, right? That's the assumption. We're using that assumption. And this is the machinery guaranteeing it could never have come out any other way, no matter how you try to factor it. So yeah, let's now zoom out. Every result today, right, uses every result today, including the Bazal identity, the key lemma, the fundamental theorem of arithmetic, traces back to one single fact, which is the division algorithm exists in the set of integers, and that's the entire engine. So here's the question driving the rest of this series, right? Which is, does a division algorithm exist in other number systems, right? And in the next video, we'll meet the Gaussian integers, right? Labeled as this. Complex numbers of the form of a plus b times I, and ask whether Fermat's question of which numbers are sums of two squares can be answered using this same unique factorization machinery. And spoiler, it can, but the proof will have a gap you will need. So thank you for watching, and I'll see you in the next video.